So welcome to this video about Ethereum 2.0 and what is Ethereum. Let's see this introduction to understand the Ethereum ecosystem and see what it's about.
Thanks to the power of modern communication, we have the ability to create technologies that are decentralized, removing middlemen and allowing users to interact with each other directly through a global network. Decentralized applications have been becoming more and more important in the past 10 years, and have the benefits of massively reducing costs and barriers to entry, removing single points of failure, preventing censorship, and ensuring transparency and trust between all the parties involved in an interaction. BitTorrent, a file-sharing network developed in the early 2000s, is arguably the first decentralized application to have been created. BitTorrent allows anyone to share any kind of file with anyone else in the world, allowing people to distribute content quickly and easily, even if they do not have the resources to pay for their own website or server. 5 years later, Satoshi Nakamoto came up with the idea of a blockchain, a sort of distributed database, and used it to build Bitcoin, the world's first decentralized currency. Decentralized currencies like Bitcoin allow people to send money instantly anywhere around the world with no regard for national borders with negligible fees. Bitcoin is increasingly being used for international remittances, micropayments, and commerce online. Decentralized applications for finance, cloud computing, messaging, and distributed governance are soon to come. Ethereum is a platform that is specifically designed for people to build these kinds of decentralized applications, or dApps for short. The Ethereum client, which we are calling the Ether browser, will include a built-in peer-to-peer network for sending messages, and a generalized blockchain with a built-in programming language, allowing people to use the blockchain for any kind of decentralized application that they want to create. Ethereum can be used to build financial applications that are fully trustworthy and transparent because they run on the blockchain. Online, cryptographically secure systems for managing property and contracts. Social networking and messaging systems that allow users to maintain control of their own data. Systems for trading underutilized computational resources like CPU time and hard drive space. And eventually tools for online voting and distributed governance. And the most exciting applications of Ethereum are probably the ones that we have not even thought of. As with all new platforms for innovation, like the protocols that underlie the internet itself, it is not always easy to predict what they're going to be used for. Gmail, Facebook, Twitter, Instagram, and the modern internet as a whole are all a result of early developments in the World Wide Web and JavaScript, the programming language of the World Wide Web, from the 1990s. Similarly, by providing a universal programmable blockchain and packaging it up into a client that anyone can use, the Ethereum project hopes to do the same for finance, peer-to-peer commerce, distributed governance, and human collaboration as a whole. Now the question is, what will you build on top of Ethereum? Hi everyone.
So far we see and we saw what it's about Ethereum ecosystem. So we can saw in the other parts specific things about the protocol specification in the Ethereum ecosystem. If you want to see a different topic that we are trying to explain today, you can go there and have the data that you want to see and understand the data that you need to understand. So let's move to the code in the Ethereum. We saw that the Ethereum ecosystem right now is in the development for the Ethereum 2.0 So we have the hoof and saw the faces. This video is about the Bitcoin chain phase 0. And in the previous video, saw interesting glossaries in the Ethereum ecosystem. And we have an interesting terminology like attestations. The other one is crosslink, also the slashing conditions, and so far we introduced this kind of glossary because it's important to know what it's about to understand the protocol, and so far to get the interest in the protocol specification and formally have a way to understand the blockchain. So let's move to the code. If you want to see the terminology and glossary, you can find out there the last video. But let's make a summary for attestations. So we have that attestations are availability both for a shared block and a simultaneously proof of stake both for a Bitcoin. A success number of attestations for the same shared block will create a closed link, which confirms the shared segment of that shared block into the Bitcoin chain. So we saw that the attestation is connected with the crosslink, and the sufficient number of attestations create this crosslink to confirm that share is a segment of to that shared block. So we can see this animation about the Bitcoin chain to understand. In summary, in the last video we saw this. So this is the Genesis state and the Bitcoin chain start. Remember that this Genesis state is not a soft fork or a hard fork state, so it's only a way and that the deposit contract start. The realization of the Bitcoin chain state, and we have the Bitcoin chain in the blue, and we have the sharp chains in aquamarine, and the lines and the arrows blue are the crosslink. It's a number of attestations to see that the sharp chains are connected in a good sense. And you start to see the yellow one that block was validated in the Bitcoin chain and in the shards chains. So you have a lot of chains in this protocol that is continuing to grow across the time to validate the longer chain and reach the consensus like the Casper protocol specification makes in the math way. So let's move in the code, and we have a lot of code. And we have here the Bitcoin chain that it's a specific folder. That is a specific folder in the hip hop project. You can find out this hip hop project in the page of Ethereum. You can Google it like Ethereum Bitcoin chain Ethereum Prims hip hop. Prims is the client that is writing in Go and Go, because in the last video saw this client, because this client have an implementation in a testnet right now. So it's interesting to see how it works, this testnet. And will be the first implementation for the Ethereum 2.0 live version in the mainnet stuff. So let's see, you download this data and you have in the Visual Studio or any kind of code studio. In this case I like Visual Studio and also use Beam and Nano. But in this, for equation proposals, we use the Visual Studio. So let's move in the code. The last video, in summary, we have that three parts are the building blocks for the consensus in the Bitcoin chain, and we have the first choice rule, that is implementation of Solovovsky protocol, a Solovovsky paper that called the GOS. And the fourth choice rule is so interesting. And we have the blockchain, because we have a lot of chains that start to make this Bitcoin chain status. And also we have the state, and we have the state chain, that is state genesis, the block 0 in this example, and then how this is start to grow, that's we saw in the animation. So let's start with the core of this Bitcoin chain. In this Bitcoin chain we can find the blocks, the epoch, feed, helpers, state, and validators. So these are the building blocks of the core state of the Bitcoin chain. Then we can saw in different ways how this Bitcoin chain works in the real world scenario. So let's see the code of the block. We have here the source code of the code, and we have the genesis block, that it's a state root with a parent root and state root and body. Then return all the signic Bitcoin block with a gem block, signature, params, and Bitcoin config. So it's important to see how this kind of block works in the Bitcoin chain. Remember that we have papers out there that explain how it works. So let's see some papers about the Casper implementation to see how it is work under the hood. So if you have a question, we are in the chat right now and we can answer your question. Ask me anything. So we have here the Casper, the friendly finally gated, but it's a paper writing by Vitalik and Gerbil Griffin. I know how to pronounce. But let's continue. We have this incredible paper about the protocol specification of Casper that is based in the paper of Solovovsky that is calling the Ghost implementation. So we can here have the introduction of Casper, that is a proof of stake fast finality system which overrides an existing proof of work blockchain. Casper is a partial consensus mechanism, combined proof of stake algorithm, research, and Bayesian fault tolerance consensus theory. We introduce our system provides some desirable features and self-defense against long-range revision, and catastrophic crashes. The Casper overlays provide almost any proof of work chain with additional protects against block reversions. So we can see that we still have the proof of work chain, that it's the Ethereum 1.0. So it's interesting how this friendly Gus or friendly Casper trying to make that this beacon chain start to grow across the network. So it's important to deep dive in this incredible paper to understand the foundation of the protocol Casper and figuring out the code that you have. So we can see the first notation that they make, and we have the hash of any justified checkpoint, that is the source, any checkpoint hash, that is the send for the S of the target, the way of the checkpoint is in the checkpoint tree, the way of the checkpoint T in the checkpoint tree, and so along. So this is the first schematic of a single block message denoted. We have the checkpoint tree. That is how this beacon chain starts to spread the message across the network. So it's an important solution because you have the wave function and the justificate chain to understand how it starts to replicate these chains. Because you only don't have one chain. Understand that you have at least 4 chains for one beacon chain in some sense. So this supermajority needs to order for pair of checkpoints. These checkpoints needs to have at least the condition that the visit time fault tolerance have. That is this number, and have published spotted with source and target B. These superiority links can skip checkpoints, and it's perfectly okay if this condition starts to spread, and show the 3 distinct supermajority links in red. So you can deep down in this interesting paper about the different approach that you can find in the Ethereum ecosystem. So let's see more code to understand this thing, and then we can figure out what it's about the Casper for choice rule. That is the more important implementation in the beacon chain. So let's move to this part, and we have the block, and the block make operations. And this kind of operation we can see that have different operation, that is verify the things that the block needs, verify the deposit data seen, verify signature, and process the data in block. Then we have the edge data has enough support, that it's also important. So the operation of the block is verify that all the data that it have, it's correct to process the block header. Remember that the blockchain name it's only a terminology, a glossary, because in reality the connection of the block is the process of the block header. So maybe the terminology could be a block header chain instead of blockchain. But the blockchain meaning it's because the journalists of Bloomberg start to spread that information in the blockchain ecosystem. But in reality, we have that the block header, it's a block header chain, not a blockchain header, a blockchain. So it's a confusing name that you can start to understand that the blocks connect between the headers of the block. So then we have how this block header is verified in the beacon state. Remember that the beacon state is how this block header connection starts to make the cross link for validate his own state. We have the process of random that we saw in another videos, that it's interesting way to the security of the blockchain foundation, and it's an interesting way to understand the blockchain ecosystem. This we can see that the beacon chain propose ADX and helpers the beacon propose index. If this instance is different of the nil, return the nil, and the proposers poof, the beacon check poof, keep, and the index, and the proposer I index. So you can see how this randomness beacon start to process the random not verified, to have a process random not verified. So remember that in discrete math you can have the equality or not the equality. So if you try to solve this, you need the randomness beacon to protect the beacon chain for the attacker or any kind of vector of attack. Then we have the other interesting glossary that we saw, that is the process proposer slashing, and we can try to replicate to see what it's about. So let's move here and start a function that is calling the process of proposer slashing. We need to put the context of this data, and we try to make this condition. Then we have the beacon state, state tried in this way, and the beacon state, that is the important thing of. Then we have the body and something else that have the block body. Then this kind of input, the beacon state, and error. Then in this data we can have different variables in a discrete math. The slashing is equals to the range of the body proposer slashings if the slashing is equals to the nil, return the nil, and these errors you have something. Then we have the int of the slashing proposer index, because we need to start understand how this beacon chain make a better state, and the number of validators start to do the things. And we have to return this in the way that we need, and thereof we need. Then if error is a verified proposer of the slashing, the beacon state and the slashing error if this is not a nil, then return and of course this is interesting, the graph. Maybe we can see the error and not verify the proposer. Then we can play a little bit with the beacon state and display it. It's because in the maybe in the protocol specification it's this for the slash validator, that is the instance can decide what is going with the beacon state. Have this slashing propose index if the error is equals to the anneal, return the nil and the errors. So it's a replicate of this code, and it's for understand how this slash shin conditions play with the code. Then return the beacon state and the nil of the instances to have a better code. And of course you have this. Then we need the function of verify the proposer. So let's move to this. We have the function of verify the proposer slashing. Of course we are in the beacon state and we need the same things here that we have here. But we need to change the context and the body. Let's connect this with the other instance, like we saw in the theorems that provide the paper. That this connection starts in the way that the protocol needs. So let's move to this beacon state, to the state of the tree beacon state that is a slashing at pb, that it's a proposer of the slashing, and so we try to verify, so the error of the proposer is equal to the error of the beacon state, the validator at index slashing proposer. If error is different for the nil, return the error, the slashing header is equals to 1, is equals to the nil, and the slashing header 1, have the header equals to the nil. So needs to return the errors, and then the new way to see this new header cannot be verified. So start to make the statement for the slashing condition if the slashing, remember that slashing is an instance that say how the consensus is reached. So we have this formation, the spec of the protocol. You can find out in the HipHook page. So we have the header to the header of something more. I don't know, maybe it could be something else. So then return the same thing with the errors that you need. I forget the other condition to start here. Maybe you can play with the proto consideration and start the slashing. Oh, maybe this is not a good way to see the render. They make logic in the header. One, the same slashing header 2, then something that needs to return the same way that we have there. And then if these helpers or something is slashing validators or validator, the proposer helpers slot to epoch. Then return something whether I need. And this is the protocol specification, and you can play with the headers, how these headers start to connect and verify that that header is seen in the root and how it's working under the hood. Then you need to process the attestation slashings, the attestation slashings, then verify the attestation slashings. Then if that attribution or attestation data is slashable, process the attestations, now verify the other head of the money, and process attestation. Let's process attestation, now verify, and verify that the attestation are indexed correctly. Then the algorithm continue, verify the attestation, the process deposits, the process pre-generates deposits, and process deposit, verify deposit, process voluntary exits. This is very nice to see. Then you have the process voluntary exits, now verify exist, and then clear it data both cache to mitigate the data that start flow and the consensus. So you can see that this slash condition are interesting. And let's see in the paper examples about this way. So let's see. If you have any question, we are in the chat for you, and we can answer any question that you have about the protocol specification. But we need to try to figure out a lot of things here. This is a complex data, and have some specific rules to understand the protocol. Well, we have the condition if two conflict checkpoints can both finalize. Policy with liveness, priority links can always be added to produce new finalized checkpoints. This data starts to connect. You decide the things that maybe don't want to decide. Some sense. And some tricky parts of POIs. Protocol safe. Then the future full. How this can be the way this router is now chain container justification of the greatest. So we can here that is the this biggest implementation don't follow the lambda chain that provides the safety, and they call in this way. Follow the chain contain the justificate chain of the grades. Okay, so this is the first foundation of the protocol, and this can help to understand all the algorithm at the attestation start. So let's see the code. Let's see more with this data. We can have the process of the data in block, how this start to connect. Remember that it's a block header chain, not a blockchain connection. So then try to verify the process random for trying to make a vehicle randomness. Then you process the counterparty, and this start to process the slashing. So we have the pseudocode definition. The process that's writing in Python that processes slashing the state of the Bitcoin chain, and the proportion slashing is equals to something. Remember that in the Python world everything is an object. So the proposer is equal to state validator registry, proposer slash proposer index. Then you need to verify the slot match. We can see that it's important for the random formation and the Bitcoin randomness. Then need to check all the headers are different, so the asset proportion is different than the proportion slash header 2. Then check proportion is slashable, answer is a slashable validator. A slashing condition means that it's not correct, so need to start another round for the slashing condition. So signatures are valid for header in proportion slashing header. We have different headers. The domain, get the domain. As we can see right now, the phone process slash condition that start with the beacon state, but with the context that we saw, we have the state 3 try. This is try 3. It's different the Python code, but makes sense in the consensus that we try to make in the block operation. Here have all the slashing conditions that need to reach the consensus, and this is important, the function of verify proposal slashing. We have right now the beacon state, and so how this proposal start for the beacon state and the validator and index. So it's an interesting way to see how this hacking code start. Then we have the process after slashing. This is interesting to see how this consensus start reaching in so many ways. So can here have the verified attester slashing. If the slashing is equals to this or is different to this because all the headers are different, this will be in this way. So the slashing attestation data returns the things wrap this condition. Then it's all about for having the slashing attestation data that you want. So it's interesting how this works because the data is different, so you start to have so different things in this code. Then when you have the data that you want, you start to spring. So it's interesting how this pseudocode starts to work in this algorithm. You start to separate the data in the slashing condition and have the slashable attester indices. So indices 1 is the slashing attestation when you're trying to encapsulate this data, have a better performance, but the function of process attestation, you have interesting way to see this data, how they start. Then we have the other party and then the process attestation, because you're figuring out how to get this data as you want. So it's the important part in this condition. So let's replicate this function, the function that have process attestation. So you are in the context, you put all the context that you have, then in the beacon state error to process all the things that you want, but you are in the last of the protocol, so it's attestation not verify. So you need any input, then if error is different for the new. Can return the new, then return the beacon states. So